In this video, we will see how to perform binary classification using TensorFlow and Keras by developing feed-forward neural networks. The problem we would like to solve is this. We want to predict the quality of red wines. The dataset that we are going to use is this file called winequalityred.csv. This is usually in the data folder in the GitHub repository. Now for this problem, the quality values given in this data set are actually numbers, not 0 and 1, but continuous numbers around the range of 0 to 10. So for this problem, since we want to do binary classification, what we are going to do is set all the qualities more than 5.5 to a 1, indicating good wine, and all the quality less than 5.5 to a 0, indicating that those are not good wines. The original data set is also available in Kaggle, which you can explore if you're interested. The first step, step 0, is to load the data. I can load the data using Google Colab, or I can also download the data if I know it exists somewhere in the internet. So I can do wget to get the data set. So it's downloading the data now. Now what we also know that the backend is a Linux shell of a notebook. So I can do, with the exclamation sign, I can run a Linux command and do ls-l to see if the file exists or not. So here is my winequalityred.csv. I can also do head winequalityred.csv to see how the first 10 lines look like. Now we can see that the first row is my headers. For example, it tells me that the first column is fixed acidity, volatile acidity is the second column, and so on. And the last column is quality. And we can see that the last column has values such as 5, 5, 6, 5, and so on. Now that we know that we have a data set that's ready to be loaded, we can actually load the data set into a NumPy 2D array. So I will specify that the data is delimited by a comma, and we also want to skip the header rows. So our data is now loaded into this variable data set. So if I print dataset.shape, I should get the number of rows and number of columns of this data. So it looks like there are 1599 rows and 12 columns. And the next question that you may ask is how to load a data set that has non-numbers. So loading a data set that does not have numbers is tricky. You probably want to either load the data set somewhere and convert all the non-numerical values to numerical values, or write some scripts to do the same. Now that we have loaded the data set, the next step is to preview some rows from the data that we downloaded or that we loaded into our NumPy variable to see how it looks. So if I do dataset 0:5 and colon, that means give me all the rows from 0 to 4 with all the columns. Now I would like to add this little bit of a complex statement here, but basically what this simply does is prints only floating point numbers with a 0.2 precision. Now if I print my dataset 0 to 5 and all columns, you will see that we don't have headers because we never loaded them. And then this 0.2f tells me that I want up to 2 precision points. So here are all of my rows, the first 5 rows, and the last column represents the actual wine quality. The next step is to prepare the output. As we discussed earlier, what we want is to have everything less than 5.5 set to 0 and everything more than that set to wine, because we have defined that a good wine with this last column equals to 1 is a wine with quality more than 5.5. Now to do this, I can set all the rows for the last column. If the value is less than 5.5, then set it to 0. And if the value is more than 5.5, set it to 1. So if I run this, now all of my values in the last column have changed now. Let's see how the values look like. So now when I print this, everything else is same except for the last column. We can now see that the last column, earlier this was 5, and since 5 is less than 5.5, this became a 0. And this one where we had 6 became a 1, and everything else has changed accordingly. So now we have converted this problem into a binary classification problem because our output labels are now zeros and ones. Here, what I've done is very interesting. If we reverse the two statements that replace the wine quality, it doesn't work very well. Say if I do, for example, if everything more than 5.5 is 0 and everything less than 5.5 is a 1, then it doesn't work, because if I set everything more than 5.5 to 0, then now we will end up with values either 5.5 or everything will be less than that. In the next line, if I do everything less than 5.5 equals 1, then everything becomes 1. So we actually should be very careful when converting these continuous values to binary values. The next step is to shuffle the rows so that we get a good mix of all the rows. Now, shuffling may be bad for reproducibility because every time you shuffle, you may get totally different results. But it is good for reliability because then you can guarantee that you don't have all the positive values in the training and all the negative values in the validation, etc. So let's shuffle the data set. A very important step after this is to split the data into training and validation set. So here's our entire table here. You can see we have the first column fixed acidity, second column volatile acidity all the way, and the last column is quality. All the input columns that we used as input to the neural network model is input represented by this symbol X. And the output that we want to predict is usually represented by the symbol Y. Now this is all the available data that we have at our hand. What we need to do is split the data for training and validation. So we will split vertically, right, over here, such that our initial rows, the number of rows we select, becomes our training data, all the rows on top, and the rows at the bottom become validation data. Now within training and validation, just like as we had in the input, we have X and Y, we have X train and we have Y train. And same for the validation, we have X valid and we have Y valid. So all the input columns that go into the model become X train on the training set, and then what the model needs to predict goes as Y train. In this case, all of these numbers will be either zeros and ones because we have converted the quality to 0 and 1. So how should we split then? A rule of thumb is to use 20% data for validation and the remaining for training. So let's get the index for 20%. So 319 examples can be the validation set and the remaining can be the training set. So let us put all the rows from 0 all the way to 319 into our validation. We extract all the columns except the last column into X and the last column only into Y, such that we build our X validation and Y validation. And then we take everything from 319 onwards with the colon sign after my variable goes into X train and Y train. Once again, Y train is the last column and everything except for the last column is your X. So let's run this. Now the question is, what is our input and output? Our input is X train and X validation, and our output is Y validation and Y train. Another question is why 0 colon minus 1 in X and Y minus 1 in Y? So the colon minus 1 indicates that I want all the columns except for the last column, and minus 1 gives me only the last column. Another question is what may happen if we don't shuffle the data? The problem with not shuffling the data is in case we had all the zeros at the beginning of the data, then all of my validation rows or my Y valid will be all entirely zeros or ones. So if we shuffle them, then we know that Y valid and Y train have a good mix of zeros and ones. The next step is to normalize our input features if needed. Not all datasets may need normalization, but if your input column values do not necessarily sit around 0 to 1, then we may need to normalize. One commonly used normalization is to use a technique called standardization. So let's see how our values are how the columns have various values. So we can see that the 0th column, fixed acidity, has values ranging from almost maybe 4, 5 to 14, 16, and most of the values are in the region 6 to 8, maybe 6 to 8, 6 to 10. Clearly, these values are not in the range of 0 to 1, so we want to normalize it. Let's also check the distribution of our output labels in X train and Y train and Y validation. So here we see that in our Y train, that is our training labels, we have around 600 examples that have 0, and we have around 700 examples that are 1. Quite good balance. And on the validation set, out of the 300 something numbers we had, we see that around 125 or 140 of them are zeros and around 175 of them are ones. So this is not an ideal balance, but that means that more values are 1 in the validation set than there are zeros. So that means actually our baseline accuracy will be more than 50%, because if our model learns to predict everything as a 1, then it will get most of the items correct and more than 50% answers correct. So here's a standard technique to normalize. Use a technique known as standardization. I will obtain the parameters mean and standard deviation from my training data and use the same to normalize my validation data. So I'm going to run this to normalize the data. And mean and STD are vectors, so we can also see the mean and standard deviation for each feature that we had. So for the first feature, the mean was 8.33 and the standard deviation was 1.72 and so on. It is very important that we calculate the mean and standard deviation from the training set and normalize the validation data set using the same mean and standard deviation. In other words, we should not calculate mean and standard deviation again separately for the validation set. Now let's look at the distribution of values for the same column, the fixed acidity column. So alright, so now we see that the numbers are distributed between -2 and 4, with most of the numbers ranging between -1 and +1. The question that one may ask is, so why did we use only the training data to obtain the mean and standard deviation? The reason is that when we are making predictions using this data set or using the model that we train using this data set, we will not know how to calculate mean and standard deviation from the new data. So a true test of the model is how it does on the unseen data using the parameters learned from the training set. So for that reason, we want to use all the parameters that we learned from the training set, not from the validation set. The next step is to review the dimensions of training and validation set. We also want to preview some of the input features and correct labels for the data set. So I'm going to print the number of rows and columns in my training, xtrain, ytrain. The number of rows in xtrain and number of rows in ytrain must be same. Same for the validation set. I'm also going to randomly print out first 3 rows of the training set, training input features, and first 3 rows of the training output labels, and the first 3 rows of the validation input features and the validation corresponding validation labels, output labels. So we have 1280 rows and 11 columns in the input. We have 1280 columns or values in the xtrain and ytrain. We have 319 by 11 and 319 in the x validation and y validation. Here's our first 3 rows in the training set, xtrain, and here are the corresponding labels. And here's my x validation, and here's my y validation. So everything looks good so far. The next step is to create a neural network model. Say we want to build a neural network model that has 12 neurons in the first layer, 8 neurons in the second layer, and 1 neuron in the last layer. Actually, to match with the picture that I have below, how about instead of this, we actually create 8 neurons in the first layer, 4 neurons in the second layer, and 1 neuron in the last layer. In TensorFlow Keras, this is how we can build a neural network that has such an architecture. So we have 8 neurons in the first layer. The number of inputs that each of these 8 neurons receive is the number of columns that we have in our data. The most widely used activation, default one, is ReLU. And all of these outputs from the 8 neurons go as input to these 4 neurons in the second layer. Once again, we apply ReLU activation. And since we are doing binary classification, we will want 1 neuron in the last layer with sigmoid as activation. Now visually, this is how it looks. We have all of our input data. You can imagine rotating the tabular data by 90 degrees such that we have these columns here, first column, second column, third column. And we also have our output labels, by the way, at the end. And now notice this gap between the two, because all the input features go to the network in a different way and the output goes to the network in a different way. So all of these 11 different features that we have go in to these 8 neurons in the first layer, from each column to every neuron in the input in the first layer. So fixed acidity goes as input to the first neuron, second neuron, and all the 8 neurons in the first layer. Same thing for the second column, and so on. Now the outputs of these 8 neurons now each feed into these 4 neurons in the second layer. And then after that, the output of these 4 neurons feed into 1 neuron that sits at the end. So then this neuron, based on all of these weights and all of these multiplications, gives you a score, a prediction between 0 and 1. And then we go back and do this error calculation to see how good or how bad this score is. If the score is very bad, then the weights that connect these various nodes need to be updated such that in the future rounds of training, the output matches more closely with the input. One question that you may ask is, what does input dim equals len xtrain 0 mean? So in the code, if you remember here, what we set was len xtrain 0 and then colon. So xtrain 0 means give me the first row and give me all columns and let me calculate the length of that. So basically I'm counting how many columns I have. We need this because each neuron needs to know how many inputs it's receiving when we are designing the architecture of the neural network. So for that reason, input dim needs to be specified only in the first layer, because in the second layer, I already know how many inputs each of these 4 neurons are receiving. They will be receiving 8 neurons. And same for the last layer. However, for the first layer, since the neural network does not know how many inputs to expect per neuron, we have to specify that. The step after that is to compile the model. So this basically checks if there are cycles in a sequential model. Typically, when we are designing sequential models, usually there are no errors. So here, when we compile the model, we also want to define the loss. For binary classification, binary cross entropy is the only choice of loss function. For optimizer, we can choose any adaptive optimizers, Atom, RMS, prop, or NATM, or anything similar. And also for a binary classification, a really good metric, the most widely used metric, is accuracy. You can also use F1 score, but accuracy is easier to understand. So let's run this to compile the model. Oh, actually, we forgot to run the create neural network model block. So once we create this neural network, then we will be allowed to compile the model. Our model is now compiled. The next step is to train the model. We feed xtrain, our big metrics, jumbo metrics xtrain, into the model, and the model calculates errors using ytrain. So if you remember here in the picture, this is our ytrain, the quality labels y, right? So it calculates error using that. In one epoch, the model scans through the entire rows in the xtrain. All the values in all the rows in the xtrain are scanned by the model in one epoch. And updating the number of epochs usually increases the accuracy of the model, because more often the training process sees the entire data set, more likely it's going to get better and better on it. Now, during training, as we train on xtrain by calculating error using ytrain, we also want to observe the accuracy on the validation data set by adding validation data equals x test and y test. So this actually should be x validation and y validation, because we want to observe the accuracy on x validation and y validation. We also want to add some callbacks, early stopping, and model checkpointing, so that my best model is saved into this file, mybestmodel.hdf5. And we also want to stop if the loss doesn't increase after 20 epochs by using early stopping. So here's our main meat operation, that is our model.fit. Takes xtrain and ytrain as the input data to train the model. We're going to observe the accuracy on the x valid and y valid. Let's set the number of epochs to 256, batch size equals 10, and then we also have our callbacks as callback A and callback B, which are model checkpointing and early stopping. So let me run the callbacks first and then run model.fit. So we can see that the model is training, and every time it's finding a better model, it's saving the best weights. So we saw that after 50 epoch, the training has stopped. The training accuracy, let's see where it started and where it went. The training accuracy, so let's go all the way to the top. The training accuracy at the beginning was 51%, and the validation accuracy was 59%. After the first epoch, the accuracy increased to 62%, and the validation accuracy increased to 67%. Gradually, we see that the training accuracy has become 72%, and the validation accuracy also became 72%. So let's go down, all the way down, to see what the maximum we had at the end. So at the end, we see that the training accuracy is 76% and validation accuracy is around 75%. So these results look fine. The next step is to check the learning curves, that is the loss or the accuracy over the number of epochs. And we can plot learning curves or check the learning curves only if we have done history equals model.fit, because this is what stores the output of the model during training. So let me check what parameters are there and what values are there in the history. So history has verbose, epochs, and steps. And what I'm going to do is print the training accuracy and validation accuracy over epochs. Okay, so I see that at each epoch, my training accuracy, this is the blue curve is the training data, it went up and it's gradually going up higher and higher. And my validation data accuracy after maybe 10 or 20 epochs, it almost saturates, similar probably for training data as well. But then if I train more, maybe after 40 epochs or so, my validation accuracy actually starts going down. So, but remember, using callbacks, we have already saved the best model probably around 30 or 35. Now I can load the best weights using model.loadWeights. So this way, now I'm back again with the model that has the highest performance on the validation set. The next step is to evaluate the model on the training data. So we already saw that the model was doing quite good on the training data set, getting an accuracy of around 76%. But just to validate, we want to do this again. Remember, we are evaluating the model on the same data that we used to train the model. So practically, this evaluation is meaningless because if we train the model on the data set that was used to, if we evaluate the model on the data set that was used to train the model, we should get pretty high score and it doesn't make sense. But just to validate that everything is working technically okay, we will do this. So we simply do model.evaluate xtrain ytrain, and then we obtain metrics. So the metrics that we have is loss and accuracy. And we see that the accuracy is 75.23% on the training data set, which is good. The next thing that we want to do is evaluate on the validation set. And this is important because now we are checking how the model does on unseen data. Now we also already saw this before in the results of model.fit function, but here we will do the evaluation using the best model that we have. Now remember, this is the real test of the model. We will evaluate the model on the unknown data set, that is the validation set. So model.evaluate x validation, y validation. Okay, so the accuracy we get is 75.8%, similar to the training set, which is good. Now, in the next step, let's check what the model actually predicts. So there's double what here. One of them should be gone. Check what the model actually predicts. An example of what the model has predicted and comparison with the corresponding true classes actually. So let's see, here's my first 5 rows of x validation and the corresponding y values. So here's my first 5 rows and then the corresponding labels, right? And let's see what the model predicts for the validation set. We provide x validation as input and the model has made predictions. Now let's look at the first 10 values. So if we look at these 10 values, we see that the confidence for the first one is 0.35. It should be 0, but it's 0.35, which is good because it's less than 0.5. The next one, the prediction is 0.96. The actual is 1. This is also good. It's thinking it's positive. The next one is 0.94, and this is 1, a good prediction. And the next one is 0.15. And this is 0.43, it's actually 0. So it got it right, but it was very close. And another thing we can do is round these predictions so that we actually also get zeros and ones in the predictions instead of getting these numbers between 0 and 1. So we can clearly see that the first 5 predictions are correct because they match with the true values. If we want to actually do a further testing, then we actually need to print more values of true and prediction to see how the model is doing. Now let's see how the model is doing by plotting the correct labels versus the predicted confidence scores. So we see that when the labels were 1, most of the time the model is predicting values that are close to 1 or more than 0.5. But there are some cases in which the model is predicting lower scores even when the correct labels are 1. Same thing for the 0 labels. That is, for all the wines that were of bad quality, most of the time the predicted confidence is less than 0.5, which is good, but there are some occasions where the model makes a wrong prediction. The next step is to ask, is accuracy sufficient to evaluate our model? We can further evaluate our model using precision, recall, and F1 score. And many times accuracy may not be the best metric to evaluate what our model is predicting. So you can calculate other metrics like precision score, recall score, and F1 score using the metrics available in scikit-learn. For example, here in our case, if we want to evaluate our model, we see that the accuracy is 75%. The recall is actually quite low. Precision is 83%, but recall is quite low. And the combination of accuracy and precision is captured by F1 score, which is 0.77. The last question is, how can the performance of this model be improved? Here are some techniques that we can use to increase the performance of the model. We can increase the number of epochs to 100 or 150. We can also increase the patience value to something like 50, 100 or something, and then increase the number of epochs as well to see if the accuracy improves. We can also add more layers to the neural networks and see how we can improve the performance, whether or not that improves the performance. The next idea is to balance the data. That is, what we want to do is create a good balance of positive and negative class values so that the evaluation also makes sense. We can also try decreasing the number of rows in the training and validation set. Maybe we want to have more data in the training set and less data in the validation set, and vice versa.